Live and ready to go. I will just quickly double check and make sure, since I don't have. Yes, perfect. I should have changed the title of this video to like intro. So I'll probably do that later. But the idea is this is meant to be an introduction stream, just to introduce what I'm going to be doing over probably the next couple of weeks, I would assume, which is going through this article from the Explained from First Principles blog. So it's a full out blog. So you can go on Google, you can just type in number theory explained from First Principles. You can kind of click into this kind of blog post here, and then you could actually see the full Explained from First Principles blog post and all the different information about it. So I'm going to be going through this, number theory explained from First Principles blog post. I have a mobile, what's it called? Sorry. I have this article open on my mobile device as well. I'm kind of like keeping track of me just kind of going through it quickly at a high level. But the stream is actually meant to be so that I can also take notes. So I should have my notes page somewhere. Well, this isn't it, but I'm going to use this for it. And we're going to open up Hack MD. And so I have, maybe I should like tag this probably. I can't even remember how to tag things. Used to do this all the time. Should be easier than this to tag it. Anyway, I should have put a tag on that, so that next time I knew what it was. How do I tag it again? Lord help me. Okay, now I'm just forgetting how to do something completely unimportant to this stream. But now it's going to be like, okay, well, now I'm just going to, Google it. So, how to tag a hack MD. Okay, so apparently I can just do this and tag it, but that doesn't seem correct. So L1 white paper, that's not gonna work. I can't remember, that's not correct. You have to put the tag between a pair of backticks to make it work. Okay. That does make sense. I just wasn't paying attention. Okay. I have to use backticks to make it work. So L1. White paper, I guess. And let's see if that works. Aha, yay. So there you go. Anyways, we're making a new note, and haha, now I'm going to do my tags right away because I'm not forgetting. And we're just going to tag it under, honestly, I'm not even sure yet. I'm trying to like have a really high level tag for all of this stuff. I don't want to call it like personal research or something like that. I'm going to do maths for now. That'll keep it reasonable for me. And I am going to try and take notes in Markdown whenever possible. So it is going to take me a while to kind of remember what all the Markdown tags are. So again, this is an intro stream, just trying to set up what I'm going to be doing like for the next couple of weeks. going over this article. So usually I just have like a, I think this is what I usually do. Can't even remember, to be honest. Just so that it's very clear which article I'm going to be working through. And then it's going to want me to, fix that. Perfect. And then generally, I just start taking notes. So as you can see here, there's actually high-level topics like linear one-way functions, finite groups, modular arithmetic, additive groups. I'm definitely going to try and stay... Come on, buddy. How small can we make you? Oh, it's around there. There we go. Nope. Really doesn't like to be smaller than that. Okay, so I'm going to keep it open to this size. It doesn't give me the whole nice view of the HackMD page. Where are we? Why do I keep forgetting how to use HackMD? There you go. So I'm not going to get the nice little view on the other side of the page. I guess I could like that. And so we're just going to go through, in general, number. I'll try and just... So I'm not going to do as much copying and pasting as I normally do. Mainly because I learn better when I actually type things out and I make mistakes and have to type it wrong and backspace and whatever else. Again, this is for myself personally so that I can learn. If other people find any of this valuable, then that's great, but that's not really necessarily the main purpose of this. I am going to go through every single word of the article while I stream. I'm also going through every single word of it on my mobile device. And that's just so that if someone actually is following along, I'm not just skipping over things that might be important. I'm also going to be adding in my own kind of comments and commentary. Sorry, I just got anxious about what if my audio wasn't working. So yeah, so I'm just going to get started. Maybe I'll even write explained from first principles. Generally, I just want to get better at writing out and spelling all of these words. Why does it not want to give me the actual spell check? Yeah. But why is it making me type it out myself? Anyways, that's weird. So I'm not going to type everything out as notes, but I will read through everything. So just getting started. This article and its code were first published on the 17th of September, 2022. So quite recently, actually, which is super cool. If you like this article, please share it with your friends on social media or support me with a donation. So it's not me. I did not write this whatsoever. So if anyone appreciates any of this work, please go to the link in the description and feel free to donate. There's a whole donation, PayPal, Bitcoin, Patreon, whatever. So please feel free. You can also join the discussion on Reddit, download the article as a PDF, see what people are saying on Twitter, or use Google Translate to read the article in your native language. So the article is very accessible across numerous platforms. I'm just choosing to read through it here and stream it because that's my most efficient way. If you are visiting this website for the first time, then please read the front page. The front page just explains to you more about the blog explained from first principles in general. And here you go, where it explains the intention of the blog and how to make best use of it. As far as your privacy is concerned, all data entered on this page is stored locally on your browser unless noted otherwise. While I researched the content on this page thoroughly, you take or omit actions based on it at your own risk. In no event shall I, as the author, be liable for any damages arising from information or advice on this website or on referenced websites. So this blog goes in and digs into various different resources across the internet. You'll notice that, as I click a lot of these, even this one, integers, for example, it's a Wikipedia link. And so I will be stopping numerous times to dig into all of the links that I find interesting, taking notes on those links to make sure I have what I need later to kind of, run through this article in the future. Okay, so preface, and there's always like prefaces you can go through. I will be going through all of them as well as I read through. So number theory is the study of integers and the relations between them. If you don't know what an integer is, an integer is the number 0, a positive natural number, 1, 2, 3, or a negative number with the minus sign, negative 1, 2, 3, etc. And it is, in Blackboard bold. So if you don't know what, like if you're ever reading a research paper and you're like, well, why do they write it like that? Apparently it's Blackboard bold, which I found to be very interesting when I was reading through some of this stuff. And it's Carl Friedrich Gauss allegedly said that mathematics is the queen of the sciences and that number theory is the queen of mathematics. What he meant by this is that mathematics, unlike the empirical sciences, studies regularities which are independent from the universe that we live in. Not having to deal with the messiness of the real world makes mathematics the purest of all sciences. I think that's pretty interesting, pretty cool, and it's probably why I continue to fall in love with math, even though I used to hate it when I was in high school. Because as the world kind of gets crazier and crazier, number theory kind of stays pure. We're kind of just finding what's already there, which I think is cool. Similarly, he must have considered number theory to be the most elegant and the purest branch of mathematics, given its beauty and that it was studied for centuries for its own sake. Or, as Leonard Eugene Dickinson put it, thank God that number theory is unsullied by any application. Of course, this changed with the advent of modern cryptography, which is, I guess, my general way of getting into number theory, and coding theory in the second half of the 20th century. Unlike the mathematicians who discovered most of what I cover or what's covered in this article, we're studying number theory only for its applications in these two fields, which will be the topics of the next two articles. So most of that was relatively straightforward, but it does get much, much more complicated. It quickly gets, pretty difficult. But actually, what I took from the preface, so I will try and maybe like take a small note, maybe H6, not sure. And just like, from the preface, so number theory is the study of integers. I can never spell, so that's just me. And the relations between them. And then I think one of the key points here is just like, okay, so if someone is unsure what an integer is, that's a nice little article. And then unlike, empirical sciences, so it's unlike empirical sciences. So, or not completely unlike empirical sciences, but in the specific way that I don't like how it's making me actually. I guess I'll learn better that way. Okay, so fixing. I don't like when it also doesn't. Anyways, it's supposed to try and fix my markdown for me. The linter is anyway. Okay, so most people that, as I come back, it's relatively straightforward. Outline. So the goal of this article is to understand how we can construct linear one-way functions using finite groups. So again, it starts going through what linear one-way functions are and what finite groups are, but I'm just going to keep going, and then hopefully it's clear as I'm going through, which have a certain property. So we'll go through with the certain properties as well. So there are two families of finite groups which are widely used in modern cryptography. Multiplicative groups and elliptic curves. The former is based on modular arithmetic, and the latter based on finite fields. So if we're going to dig up what finite fields are, okay. Oh yeah, it does dig into it again later. So I'm just gonna not dig into it now because it does dig into it later. It does both, I think. Yeah, so prime numbers play a crucial role in both. We'll study these topics in a somewhat peculiar order and also take 2 detours which will play off on our journey. So this graph is trying to explain like the various chapters of the article and how they build upon one another. I find the graph quite interesting, but obviously you learn about linear one-way function first, you learn about finite groups, and that kind of tells you, modular arithmetic has to do with additive groups and prime numbers, and it gets quite complicated quite quickly. So again, I'm just going to continue. Again, this is just an intro stream. Once I get to like the actual math part, I will stop because I haven't gotten that far on my mobile where I'm doing things on my own. So I'm going to be doing both on my own and streaming. So since it's easy to get lost in theorems and proof, I definitely agree with that part. I start this article with introducing and motivating the concept of linear one-way functions so that we never lose sight of our goal. Afterwards, I cover finite groups in the abstract in order to establish the terminology that we will use for the rest of the article. That's about how far I've gotten so far. Establishing a mental framework first also helps us to process our observations later on. Additionally, proving properties in the abstract saves us a lot of work when looking at multiple examples. If you read about these topics for the first time, feel free to jump ahead and play with concrete examples. I have not gotten there yet, and that's what I'm hopefully going to be doing when I'm streaming, is like going and playing with the concrete examples in the article, hopefully building them out in Rust and doing that here live before understanding the theory behind them. So I'm currently trying to understand the theory, which is very complex. I think doing the examples first would be much easier, but again, trying to do both at the same time and see kind of where I meet in the middle. If you really want to grasp the math behind modern cryptography, you likely have to read this article more than once anyway, which is kind of what I've kind of taken on, being like, okay, I'm going to have to read the article multiple times. So I'm reading it once, just very quickly on my mobile device whenever I have time. So like literally between watching anime with my wife or kind of, whenever I have 5-10 minutes to kind of read the article, I just go through it at a high level. And then streaming it here will be like a second time, but also obviously I have to have other time with the examples as well. The reason for covering modular arithmetic and multiplicative groups before prime numbers is to get as far as possible before the math gets more challenging and to understand why prime numbers are so special. After learning about elliptic curves, I cover the best known algorithms for breaking our linear one-way functions in a bonus chapter before concluding the article with formal proofs for basic group properties as an appendix. Awesome. So in this outline in general, there's just a lot to kind of go through. Nothing for me to take notes on yet until we probably get to linear one-way functions. But I will still go through kind of the contributions and the math aversion side of things, because reading through this really helped me to understand probably what's going to be happening and also like what to expect. So like this part down here. But anyways, there already exists plenty of textbooks and blog posts on number theory. See below for some recommendations, which I'm probably going to have to read through at least the blog post and maybe even buy some textbooks to fully grasp everything that's going on. But the writer is saying they weren't sure if they should write their own, since future articles will require a thorough understanding of number theory, and my ambition is to explain things from first principles. They proceeded anyway. So they're going to write more articles in the future, which is super cool, and this is kind of just the start. So for me, it's also making sure I understand this article thoroughly so I can understand whatever articles come up next. So, they're saying this article specifically is unique because there's a focus. So number theory is a big field with many advanced concepts. This article focuses on aspects which are relevant for modern cryptography and coding theory. As you'll see, almost all theorems mentioned in the article are being used later on. Notation. This is probably the coolest part of this article, and every time I read a research paper, I only see one type of notation. So there's two notations used in group theory. And this person's saying they haven't found any other source which constantly provides both. Not having to translate between the two yourself reduces your cognitive load. I mean, I agree. I mean, it just makes it so easy to see the way it's written out in additive or multiplicative notation, and that's been helping me like learn a lot just from seeing the way things are written. So intuition. I went to great lengths to complement formal proofs with more intuitive explanations. I'm excited to get into more of the proofs and to see that. While formal rigor is important, nothing beats an intuitive understanding of a theorem. Completeness. Apart from the chapter on elliptic curves, I took no shortcuts when explaining why things are the way they are. Therefore, this article contains the complete proofs of almost all covered theorems, including, and they give a bunch of proofs, and they're saying they haven't found this online outside of PDFs. Again, this is where this whole stream is going to slow right down when I actually try and go through these proofs and theorems. But it's going to be interesting. We'll see how that goes. I am no expert in discrete mathematics or number theory or any of that. So interactivity, depending on how you count them, 40 proofs, which I published on a separate page. So maybe, oh wow, this is so interesting. I feel like I want to note this down in the preface just so that I come back later and go through it. Just like stuff at the beginning of the article. So, tools, proofs. Whoops. Okay. And then it's talking about math aversion, which is kind of like how I used to be or how I am. But this also makes me kind of hopeful, as I read through this. So it should be no surprise that this article about math contains a lot of math. If you're afraid of math, which, used to be me, then see this article as free exposure therapy session. On a more serious note, number theory is quite different from the math you endured during high school. Number theory is mostly about understanding why some properties follow from others. You won't have to calculate anything yourself. This is what computers are for. So that's whenever I realized in high school that you can use computers for all your math, I got very interested. At times, the notation can seem daunting, but this is actually a problem of language and communication, not math. The situation isn't made easier by the fact that different notations are used to talk about the same things. So again, additive notation and then multiplicative notation. Well, I tried to keep everything as unconfusing as possible. This is an aspect that I couldn't change. So again, this person that wrote the blog explaining that if you're kind of afraid of math, you're going to have to do math. And I am generally afraid of math, and so I'm excited to be forced to do some math. Why proofs? Actually, I do have to check my phone real quick. Sorry, just dealing with family fun things. Y'all are funny. My siblings are funny. That's the way they are, and I love them. So, no harm, no foul. So why proof? There's a big difference between understanding how something works and understanding why something works. So for me, I have been focusing much of my career, like researching, learning, teaching, on pretty much focusing on why things work. Like, why does this happen? Why, sorry, how something happens, like how everything works. And I think proofs are very interesting to actually prove why it works, not just how. So in mathematics, answers to why questions are called proofs. Okay, proofs explain a statement is true by showing how the statement. Apparently, my assistant needs to download things. Very distracting. Okay, so like, and then maybe like show definition of proofs. So proofs. They explain why a statement is true by showing how the statement can be deducted from an already proven statement. It's called theorems, and statements can be assumed true with axioms. So to me, it's pretty important to understand like what proofs are and like why we use, like why they're used. Again, I've only like written out maybe like 10 or 20 proofs in my life, so a lot of work to do on that front. But this is kind of again where we're starting at. So if you want to understand only how modern cryptography works, you can skip this whole article and read the next one. But if you want to understand why modern cryptography works, there is no way around proofs. Even if you find them overly formal and tedious, which I do. But of course, you can always ignore answers to questions you would not have asked. And I like asking all the questions. I don't like ignoring the answers. And so here we are. Okay, further reading. The two most important sources when writing this article were a computational introduction to number theory and algebra. So I am going to take notes of these. So I'm just going to, I guess, write like additional resources. And then just, there's 2 of them. And I'm just going to copy the link. I did not copy the link appropriately. Is that going to work? Anyways. And the handbook for applied cryptography. That's, oh my gosh, you can just read the whole book. That's crazy. U Waterloo, yeah. That's amazing. So again, like, I feel like I'm going through this article, but I literally could just spend a few months reading through an entire book that's here, right? And like that would be useful for me probably. So I have no clue where going this article is going to take me, but the whole idea is if I at least live stream myself reading through the entire article and taking some sort of basic notes, I will have at least the next time I go through the article a very, very good place to start, understanding where I'm lacking a lot in my understanding. I guess usually I was keeping it H3, so linear one-way functions. So this is when you start getting a tiny bit of math, and I'm going to have to start writing a little bit of lexicon or a markdown notation. And so I like one of the things I want to get better at is writing markdown like this. I'm not good at it, like just generally. And so I am going to take my time during taking notes here to, not today again, I'm just doing an intro. I will change the title of this. So starting, tomorrow, I'll go through like the definitions. Definition, and then I'll just be like, a linear one-way function is a function computing the output. And like honestly, doing big A, I forget how to even do big A. Like big A. Yeah, I forget how to do. But I used to like have like. Okay, so and then like the best part about it is when you start like copying and pasting, like this type of stuff into. So now I know big A is $sign to the right, and then small a would be $sign to left. So with the output A, oh my gosh, the output A is a linear one-way function is a function where computing the output A from A. Oh, why did you do? Oh no. A from A, but it doesn't. Oh, sorry. A from. And there's a way to make it so that this ends. Okay, so then even here I have to like copy and paste this. And this is the stuff that always took the longest when I was doing stuff. So is it F of A equals A? If I type after this, it works. So why does this from I'm remembering how annoyed I used to get with Markdown. So literally here I have A and it wants to put from all weird and lowercasey instead of see, it wants to write it all as the same word. I need to like remember how to use Markdown before I start using it. Oh gosh. I think this is just an issue I'm having currently with. Okay, now if I now it doesn't want to. Okay, I'm actually curious. A linear one-way function is a function where computing the output I'm just going to start copying it. The output. What if I just... No, it always does the entire thing. That's sad. Oh, that will cursive everything up until the $sign. Haha, I did it. See? And that, okay. I'm just silly. I forget the input. But then once you do it a couple times, it takes you a long time and you remember for next time. The linear function is a function where computing the output from the input is efficient, but finding an input A which maps to a given output A is computationally infeasible. Function where the input where A is an integer whereas where A is an integer and there exists, where's that there exists symbol? See, I forget. And there exists an operation. I love it. Yeah, now I know what it is for next time. There exists an operation so that the function of A, with the input of A plus B equals the function A and operated on function of B. Okay. Awesome sauce. Now we have our definition at least. And there's some properties here which help explain like what's actually happening, which is helpful. And writing out, since this function where you have the input of A and B to equal to A is 1 and B is 1, then there has to equal, a function where you have A here is 1, you're going to have some operation, and then it would equal the function of A and the function of B when operate on each other. And then therefore it's saying if you generalize it to f of n, it equal to f, 1 plus 1 plus 1 plus 1, plus n times equals the f of 1 operated on, the f of, whatever, many times it needs to, n times. The inputs can be called scalars because they scale the output of the function by any linear factor. So I guess, as you use n equal to 2 or 3 or 500, it would scale in some linear fashion. Again, that's where there's like different pieces of information. So like a scalar is an element of a field which is used to define a vector space in linear algebra. Real numbers or generally elements of a field are called scalars and relate to vectors in an associated vector space through the operation of scalar multiplication defined in vector space, in which a vector can be multiplied by a scalar in the defined way to produce another vector. Generally speaking, a vector space may be defined by using any field instead of real numbers, such as complex numbers. You get some like complex idea there. Then scalars of that vector space will be elements of the associated field, such as complex numbers. So again, it goes from simple ideas to much more complex, topics. We're getting to notation and everything else. So I'm going to stop there. Again, this is just an intro video. I am going to kind of start on linear one-way functions next time. I do have a lot of work still to do on my own to make any of this content even useful for myself. So yeah, that's about it for the intro video, and I'll be back next week to go through this some more.